Okay. For on record, can you repeat the question, Yogendra?
So how we will know means whether this graph fits a polynomial function. We will try to fix the line in linear. So how we will able to know that this is polynomial or
Right. So this is a specific problem of known as model selection. So what the questions, just to simplify the question for those who may not able to get it, is like, how do you know like what to fit, whether it's a line or a parabola or a sinusoidal function or a degree 3, degree 4, degree 5, like so this is like in general, if you want to simplify, how do you know where what is the model that you want to fit. So I will try to talk about the terminologies. I will try to clarify them, and then we will discuss it, how to choose the model. Right? Any other question before we start the class? Any other question? Okay, fine. If there are no questions, but still you can. I have asked you to join my Google Classroom, so you can post your questions there, so that everybody can get a track of it, like the thread of questions and answers, which I will be addressing there. Uh, just for a quick check, one of you can let me know whether you can see the slides or not.
It's a
You
black
can
screen
type
for me.
yes or no.
It's a black screen, sir.
It's a black screen. Okay, let me. Black screen. Just a minute. Still,
It's visible, sir. We can see the power.
Now it's okay, sir.
it's visible. Fine, fine, fine. So, uh, the rules are same like yesterday. What I told you yesterday. If I get disconnected, please one of those two guys give me a call, which I have said, right? If you are there, fine. So yesterday, like just to bring you all of on the same page, we had come up with some data set, and the trick was to form a data set that we have just thought of some sinusoidal function, and the sinusoidal function was defined between 0 to 1. We have taken 10 uniform values between 0 to 1, right? And for all those 10 values, we have find out what is the sin x for that 10 values. So that's how we can get x comma t pair. So x is my any one value, right? So x is my any one value on the uniform scale. Let's say this is my x, and corresponding sin x is this value, right? This is sin x. Now you add some noise to it. This is what we going to get, this blue dot, right? So this is how we got these 10 points. And now I ask you to just forget that how we form this data set, and you have these 10 pairs now only, right? So and you represent these pairs as xi comma ti, right? Xi comma ti, where ti is a function of x in terms of sign, but we don't know, right? As I told you, you need to forget it. So you have these 10 pairs x comma t, and I ask you to just come up with some possible choice of your model, right? Model means here I'm saying function in mathematical sense, but if I just ask you, that function can be of anything. It can be discrete function or continuous function. So function is a very general term, right? So then you try it, just because the name of the slide itself says that we are doing polynomial curve fitting. So then I asked you to just think of all polynomials which can fit to this data, only polynomials. So there is a huge universe of the functions, and in this huge universe of functions, we can have like so linear functions, means to say line, then sinusoidal. These are polynomial class of functions. Then I can go beyond this polynomial class, right? And all these possible functions which I can fit to this data set constitute a hypothesis set, right? So there is a one set known as hypothesis set, and this hypothesis set says that I have all those I have like different choices of functions. One can be line, and line again are infinite lines. It is not one line, because line is defined by the slope and intercept, right? So this is one line, second line, third line. So there are some infinite lines. Again, there are some infinite parabolas, right, with different parameters. Then some another class of functions. So these are the polynomial class. So similarly, some discrete functions you can fit to it, and all those choices which you think of to fit your data set constitute a hypothesis set H, right? So I just for this beginning class, I said that you need to just focus on polynomial class, right? So your hypothesis set is what? Only polynomials, but of any degree, right? So you have restricted your hypothesis set, and you are just looking to fit a function from polynomials only, right? And these polynomials can be of any degree, from degree 1 to degree 100 or infinity, anything. So your hypothesis set is here what? Only polynomials. Then we tried a line, and I said that line can again be infinite lines. So you are choosing best line. Then you think of to choose parabola. Then you are taking best parabola among all parabolas. What is the definition of best? We have discussed it yesterday, but again I will come to that point. So then we said that we need to choose the polynomials, right? So in general, you can write a polynomial in this form, right? W0 plus W1x plus W2x square, and keep on going, and Wm to the power xm. So it is a degree, the polynomial degree here is m, and m is a general term. If you put m equals to 1, so you are seeing only line, right? If you take m equals to 2, you are seeing some degree 2 function, quadratic function. And if you see m equals to 3, then it is somewhere some cubic function, right? And you keep on increasing your m. So m is general here. If somebody say I don't want, I want my m is 0, then you are just fitting a constant horizontal line, right? It is just a constant horizontal line on x and y scale, right? So these are your some points, let's say, and you are fitting some one of the any horizontal line, because this W0 will tell you only the intercept, and it will be constant for every value of x. So it means it's a horizontal line, only horizontal line. And if somebody says, no, I just want to go beyond the capacity, I want to increase the capacity of a model. So it means you just want to increase a degree of freedom. So what I mean to say, the degree of freedom, if you say that I will take only W0, so it means you are saying, okay, my hypothesis, out of my hypothesis set, I will fix my model, and that model is only are having a horizontal lines, right? Which is that horizontal line which fit to my data is the another the topic to discuss. But when you say I take W0, so it means you're just focusing on horizontal lines, and that which horizontal line will you want to take, that will decide by the value of this parameter. If you say W0 equals to 1, it means the horizontal line will cut this y-axis or t-axis on 1, right? Now somebody say, no, I don't think so, that this is very restricts the hypothesis. It has a lot of constraint. I want to just increase the model capacity. And rather than saying only horizontal line, I can say any line. So now if I say any line, so I have two parameters now, W0 and W1, right? W0 is an intercept and W1 is a slope, right? So in that case, I have 2 degree of freedom. It means it can cut anywhere and it can go in any angle, right? So it has a 2 degree of freedom. So I'm talking about any line. I hope this is clear. What is 2 degree here, right? Fine.
Sir.
Okay, you can just type in so that it will give me a quick feedback, right? Each of you can respond in a chat box. Cool. Fine. So now third person may come and say, I don't think so that line is a good choice. You should choose a quadratic function. Then you are trying your best. Out of infinite quadratic function, you are choosing the best function which suits to your data, which fits to your data, right? And I just said that this is the next slide and other slides where I'm going to find out how to choose the best line or how to choose the best quadratic function. But still the question is what model you are choosing is the first question. And out of that, what one model, when you choose, you freeze your choice that I'm going to choose either a line or a parabola or only a horizontal line. Once you freeze your model, then the second question comes, what is the value of the parameters in that model? For example, you choose a line. The second question comes, what is the best value of the parameter? It means what is the intercept and the slope that fits to your data, right? So first choice is what is a model? It means what degree you are choosing. Either it is degree 0, degree 1, degree 2, or degree m. Once you freeze the choice of a model, then the second thing comes to you to find out the value of the parameters of that model. I hope it is clear, right? This is a very valid and genuine point here. Can you quickly write yes or no? Two choices, what is a model and what are the value of those models, right? Fine. Very nice. Very nice. So in case everybody is typing yes and one of you may think that you don't understood it, you can unmute yourself and explain, let me know, right? Don't get peer pressure that everybody is getting understood. Why I have not. You please, you can discuss it here, okay?
Sir, what factor decide that value of m?
Yeah, that is a model selection. So I said that there are two problems. One, what is the model that I need to choose? And second problem is what are the values of the parameters of that model? So I have not asked, tell you the answer of that, right? You need to first frame the problem in your head. Model selection is the first problem and optimization is the second problem for that particular model. Like what are the values of that model? I have not told you like how to find out the model. And it is just and whole machine learning depends on this question. What is a model? So it's not an easy answer. We have to go through all the semester to answer this. But knowing a problem is very nice, right? Fine. So what are unknowns here? I don't know what is the model to fit and how to find out unknown. So there are two problems here. Let's say some magical powers comes to your head and you found out that, okay, I found out that line going to fit to this data set. The thing is how to find out the values of the parameter for that line. Like what is the intercept and slope of that line? So this is a second problem. You are actually looking for the values of the parameters. So somebody said, you just choose a criteria and you just improvise that criteria, right? You just improvise that criteria. So criteria may be in terms of like error, and you just keep on reducing that error. Criteria like cost function. This is known as basically cost function if you learn deep learning and all, right? So in general, people say that this is a cost function. So if you once you frame the cost function, then you have to improvise over it. So you need to find out the value of intercept and slope for those for that cost function, which can reduce that to zero, right? Or not always zero, but which can reduce at the maximum, right? For an example, these are the 2 points. These are the 2 points, and I have only one choice. I can choose only a horizontal line. What do you think? Voluntarily, can anybody answer? What do you think? Which is the best line that can minimize my error for these two data points? I can choose only horizontal line. Remember that. So the value for this is, let's say,
Straight line
5
passes through both of them.
Just a minute. This the value of first point is 5 comma 1. The x is 1, t is 1, and let's say this is 4 comma 2, right? So this is 4 comma 2. So x value is 4 and t is 2. So I need to find out which horizontal line fits best to this data set. What do you think? So my model selection, I have already done that, right? So I have done the model selection. So my model selection is that I am going to choose only W0. My M value will be 0. Somehow randomly that comes to my head. Okay. So somebody has answered it. Oh my God, I can't see. Okay, this is there. Right, exactly. So it goes between these two, which can fit. But this is an easy case, right? When you know that I have given you 2 points. Now, what if there are 100 points, right? So, like say these are the all points, and I need to choose the horizontal line among them, right? So it means you are just choosing. You are creating some criteria, forming a criteria, and then you are minimizing it. Here you said that it is 1.5. So my actual line goes from 1.5, but still you can see the error is not 0 here. But the error is minimum. That is for sure. Intuitively you have thought of. But if you just deviate a line here and there, it may give like some error which is more than this line, which is going from 1.5. So when you draw the cost function will be somewhere like this. Just see it very carefully. So my cost function will be on parameter. What is my value of parameter? So here the value of parameter is W0, right? And this is a cost C. So if my value of parameter W0 is 1.5, as you said that line will go from 1.5, then this cost function will be minimum somewhere at 1.5. And if you just go deviate from 1.5, it go again up. But I'm not saying that this is 0 here, right? So because there is some cost involved, right? So the cost function look like somewhere here like this. And you need to reach this point somewhere here. And this point says that you can achieve it when your W0 is 1.5. Is this clear? Visualization of W0?
Sir, could you repeat it, please?
Okay, I will try to repeat it again. Hmm. So I said that what is the best line that you want to choose, and you have just come up with the right choice that it was 1.5. Then I was discussing. Then geometrically, you can see the same thing like this. So you have only one parameter, right? You agree with this, right, Pravalika? You agree with this that I have only one parameter, that I need a horizontal line. So where it should cut. So it should cut either 1 or 1.5 or 2 or 2.5. So I have only one parameter W0, and I need to find out the value of this W0 only. So this W0 can continue from 0 to infinity or minus infinity to plus infinity, right? Because I can intercept at minus infinity and I can intercept at plus infinity. So my W0 vary can plus infinity to minus infinity. One thing. As you said that the best line is 1.5. If you intercept other than 1.5, your cost will grow, right? That is not the best line. So if you plot it that way, so let's say this is 1.5. So here my cost will be minimum, but it is not 0 because my line is not going through the data points, right? So it is the cost involved here, right? This is the cost involved here, because it is not touching these data points. And what is my best line is still away from the data point. So these 2 points, when you take E1 and E2 and square them, it will give some value. Let's say that value is this. So now if you just deviate away from this 1.5 value of W0, your cost will grow, right? Let's say it is a symmetrical thing. So you can have this is the function, right? This is a function of W0. And on this axis, this is a cost. So if you are away from 1.5, your cost will grow. Whether you are on the up or down of the W05, it depends whether you are left or right of this point, 1.5, right? So this is a cost function. You can visualize this cost function like this. So cost function you always draw in a parametric space. So what is a parametric space here? W0. So somebody is asking, sir, cost function is equals to error function, right? You can say that. So we will not fall into this ambiguity right now. It may be possible some textbook may say something else about it. But for my purpose, yes, you can say that it is a cost function. It's okay. Once if they make some other sense, I will clarify it to you. Right now, you just take it as a cost function or error function. So you want to minimize this cost function, right? You want to minimize this thing. So one thing is like you have to form a cost function. So this is your cost function, which we have discussed yesterday. We have said that we will take the sum of square of all the errors. So I'm not going to go into that detail again because we have discussed it yesterday. I want to minimize it, right? So because it's a quadratic function of degree 2, it is a convex function. It is a convex function. And convex function means that it seems like this, and it have a unique minimum, right? It have a unique minimum. So there could be a function which can have 2 minimums, right? This is one minimum, like, and there is another minimum, local minimum. If you see between these 2 lines, this is the minimum. This is a local minimum for this between these 2 lines. And if you see between these 2 lines, this is the minimum. So this is a local minimum. What is a global minimum? This is a global minimum. Among these 2 minimum, the function could be having where those 2 minimums are the same level, right? So these are convex functions. If a function like square error, it has a unique. If it has a unique minimum, then you will always uniquely get the parametric values. For an example, every time you minimize this function here, you always get 1.5 only. From wherever you start on a function doesn't matter, because it is a very unique minimum. But if this function could not, if it is not a convex function, let's say this is this function here. If you start from here, you get this nearest minimum. And if you start from here, you get this nearest minimum. And 2 students can get 2 different values of the parameters. But fortunately, what I am discussing here is a convex function, and it is having a unique minimum, right? So any questions so far? Any questions?
No, sir.
So fine. I just told you that we are discussing cost function, and in that cost function, we need to minimize that cost function, right? And that calculus come directly into play, right? Once I say I want to minimize a function, you are good at it to minimize the things. Take a gradient and put it equals to 0. And if you are lucky, you will get solution in one shot. I will clarify why I'm saying if you are lucky. Right now, just take it that it is a convex function and you are good at calculus. So what you can do, you just take a gradient, put it equals to 0 and minimize it. I hope you have done this maxima minima problem in your intermediate while you were preparing JE, right? So all of you remember what is max min thing of this in the calculus. So this is the same thing. So now if a function is given to you, you just take the gradient of it and put it equals to 0. just to be very precise and not to confuse you, there are very specific class of functions where you can take a gradient, it equals to 0, and they give you a solution. So this is that example what we are discussing right now, it falls into that category. I will expand the expand the like space, but right now you take it that we can take a gradient of a cost function and put it equals to 0, and it will directly give me the value of a parameter. So my cross questions here, I am going to get a value of a parameter of what? Bhargava, sorry, B Rangavan. B Rangavan, can you unmute yourself?
Yes, sir.
What is a parameter here? I'm frequently telling parameter. What is a parameter in this example? What I'm discussing now?
So the parameters with respect to x.
No, you need to name the parameter. What is the name of the parameter in example?
Sir, I didn't get it. What you're asking?
Okay, fine. Unmute yourself. Can you raise your hand who just got my question? Or in type like in this window if you want to answer it. Okay, Rahul, you want to go with it? Can you answer? Can you unmute yourself, Rahul? Priya,
Yes, sir.
what is the parameter here?
Sir, W.
W0. Be specific.
Yeah, W0 for a horizontal line.
Exactly. So this is W0. So my parametric space is of what dimension? What is the dimension of my parametric space?
It's one dimension, sir.
One dimension, not two, Prabji. So it is one dimension because I am having only one parameter here, W0. So if I am finding out a line, so then I may be choosing two different things, like what is the intercept and what is the slope, right? Then it would be two dimension. You understood, Prabdi? So this is then my parametric space will be of two dimensions. So right now I am in one dimension. So if I am in one dimension, my cost function will be a curve. And if I'm in two dimension, my cost function will, how it will look like? Sahana and H. If I am in two dimension, if my parametric space is of two dimension, what is how my cost function will look like? Pravalika. Can you just show your presence? Are you there or not? Or having a good breakfast? Pravalika, are you there? Fine. Well, Rupesh is saying it is a spherical type, not curve. Not curve. Curve is in a single dimension. So I am plotting my W0 with respect to cost. I'm getting a curve. Yeah, sheet. I don't know whether it's a very formal word or not, but I can accept your answer. Vedant Keshav. So it is in sheet, or it's kind of a surface. I mean to say it is a surface, right? So not plane. Plane is not exact word. So plane is a specific word. Plane is always straight, like a board. Plane you can't say. Plane is a board, right? So it is kind of it could be kind of an umbrella, right? Just umbrella sheet, black sheet. Let's see that part. Plane is just a board, right? It's a straight linear part. Bowl shape, yeah. Bowl shape is fine. Bowl shape. So in short, in general, it is a surface, and surfaces can be of any type. It can be bowl shape, it can be a plane, right? It can be convex, concave, anything. You can imagine any say, or you just fluttered your wave your blanket in the air, whatever the formation comes, that is a surface. Fine. Okay. So now you got the crux of what is ultimately we are doing. We are having a cost function and we want to minimize it. Cost function always we draw between the error and the parameters, right? So if my parameters is of two dimension, then I am looking for like intercept and slope, right? So this is my W0, and this is my W1. So for every, this is the point. Actually, I'm saying this is my intercept, this is my slope. And if this is a line, I get some error here. For every point, I am getting some point in this z-axis, right? And it will give me some surface, right? It give me some surface. And I want to minimize it. So this is a minimum point, let's say here. So I will say the point, the intercept should be this, and the slope should be this, right? And corresponding to this, this is the error which is minimum. So my parametric model for a line or for my model W0 and W1, this is the best value that I can get because it is having a minimum error on the surface, right? This is what you're going to get. Okay, so I just I have taken you like long, very stretched into the future, and this is what we are going to discuss again in like another 10-15 classes in very much detail. So please go through the sensitivity chapter. Not to worry, I will come back to these things again. Fine. So then the question comes like what is how to select a model, as this the question came before in the just in the beginning of a class. How to choose a model, right? You can say that my line could be horizontal only, or I can take a line. So these are the whatever I'm showing here. It is the best model among the infinite choices. So if you say I want to choose only horizontal line, so this is the best horizontal line which can fit to your data here. If you say I have a 2 degree of freedom, W0, W1, it means you're talking about line. So this is the best line among all the lines because this is also one line. This is also one line, right? But among all the lines, this is the best line which is shown here, right? So this is the best line. And for degree 3, this is the best curve. And you see, like, just for the illustration purpose, if I could have magical power in my head and I thought of to choose a model of degree 3, then I would be very, very near to my sinusoidal function, which I never know, right? I told you in the beginning of this course that you have always thought of that you don't know a true function. You can always see these blue dots, but never this green one, which actually originated these blue dots. Now you started with these blue dots and you never know this green function, underlying true function. So when you choose accidentally of degree 3, you found out that because we know, right? Just for illustration and because for learning purpose, these examples are given, that you see that if you take m equals to 3, it is very near to your true function, which is sinusoidal. And if you go m equals to 9, and it is really a very ziggy function, which not at all seems to be a true function, right? Okay, so there's okay, you discuss among yourself and then get back to me tomorrow. So then my question to you guys is, what do you think, which of the model is giving me less error? Which model? I have shown you 3 models, right? 4 models. M equals to 0, M equals to 1, M equals to 3, M equals to 9. Which of the model is giving you the least error? You need to answer in terms of M, right? Okay. So I think there is a need of bit clarification here because few answers are coming M equals to 3, but answer M equals to 9 is right. M equals to 9 is right because anybody want to answer why M equals to 9 is right? Anyone? Those who know.
First function.
Yeah, Yogendra, please go ahead.
Minimum error functions.
Why? Don't say minimum error function. My question was which of the model is giving minimum error, right? So you need to answer why m equals to 9 is giving minimum error.
Sir, because it fits perfectly. The curve passes through all the points, hence the error should be 0.
Yes. So the answer is because the curve is going through every data point. And if you see here, what is the error for this point? This point is on the curve, so it is not far. For example, this point is not on the red curve, so this is the error. So this point is not on the curve, red curve, this is the error. Likewise, if you see m equals to 9, every point is on the curve, so it is on the curve, so error is 0 for every point. If you add all zeros, you will get 0. But if you see m equals to 3, this is error. This is again some very small error, but it is not 0, right? So these points still contribute some error, and when you add them, it will be a some amounts. Though it is subtle, but it is something, but it is not 0. But when you take m equals to 9, it is exactly 0. So that's how when you say that, because this point is going through this curve is going through every data point, and the only measure you have at your hand to judge is training data set only, right? Because you don't have any other way to find out in the world whether how I'm doing it. The only measure is you have your training data set. So you just compare it with the training data set, how my curve is going, whether it is going through it, every data point or not, right? So what does this mean? If I show you these 4 figures and you are sitting for Amazon interview, and some interviewer asks you which of the model you should choose for your predictions in the future, what should be your answer?
M equal to 3.
Why?
M equal to 9 is overfitted. It's specific for just
What
this
do you mean?
example. M equal to 3 might be useful for general
What
purpose,
do you mean
has
by
lower
overfitting?
overfitted, as in it is more specifically suited just for
No,
these specific points. If any other data were given, then it would not fit for them
but
accurately.
can you just shut? So I am saying you need to just answer that what I'm asking. Don't overuse the terms, right? That is my job to explain the terms. So you have used overfitting because it is overfitting m equals to 9. What do you mean by overfitting? What do you mean by overfitting?
It is
Yeah.
very specific to
Go
that
ahead,
example.
what is overfitting? No, this is not overfitting. What is overfitting? Anybody in class? What is overfitting? M equals to 9 is specific for the training data set and won't detect slightly deviated data sets. Oh. So actually, just asking like what is overfitting is may not be absolutely ideal question, but how overfitting like create a trouble to you? Can you answer this thing? That it is more like general now. If you take amicus to 9, how it will create a trouble to you?
Let's say like we have some other data like which is like we have a new data set point, then on that data set point this m is equals to 9 will give like can give a huge amount of error there, or that can be a like that this data can treat that as an outlier.
You mean to say data set or data point?
Data point.
So you have now unseen data point, let's say x11. So I have already x1 to x10, right? And corresponding t1 to t10. Now somebody gives you x11, which you have never seen in your training data set.
Yeah.
Now predict T11 for that. For X11, you want to predict X11, T11. So what can you now clarify what is T11, what you're trying to say in this context?
Yeah, let's say, let's consider these four scenarios. Like in m is equals to 0, what will happen? We know that this T11 will we have some new data point. We know that this data point will have some distance from this line, and it has fitted it in such a way, whether it is above the graph, or let's say above the line or below the line, it will give a mean error, let's say around that, the same error that is giving around the average.
No,
And m is
no,
equal to 1, the same case will be there.
no. That is not like what I'm looking for. Anything? Anybody else like want to just put anything on this view? So see, just try to see here. For an example, this is your X11, right? If you have taken, so let's focus everywhere on this same point. So this is the same point, right, for X11. So some guy have used this m equals to 0. He might have predicted this point, right? Yes or no? Can you quickly type yes or no? If you have, what do you have? Your x equals to 0? Yeah, fine, cool, very nice. And if you have taken m equals to 1, then you could have predicted this point, right? So this is your T11. And for this is your T11. And for this, somewhere here, let's say this curve goes like this, and this goes somewhere here. And this is the same axis. I mean to say very far from the original, right? So you can see that you can do very bad on like unseen data set. And this is what overfitting cause a problem. Overfitting is a delusion, right? It's a illusion for you. You seems like you are doing very good, very good, but on what? On only training data set. But when it comes for you to, like, you are a very pro in mugging, right? If you mug everything in a class, let's say, don't take it otherwise, but it's just an example. This is an overfitting example, and I think it is a perfect example. So if you mug everything that the teacher write on a board, and he just deviate, he just twist a question bit, right? Once he twist a question, and if you are good at only mugging, right, your generalization is poor and you just only know what is written in the copy, then you are unable to answer it. Your answer will be very drastic and you may get 0 there, right? Where you may not be lying near to the fact, not near, where very far away from it. Similarly, this thing is, if you take m equals to 0, the original would be this is a true value, and what you predicted is this. So the difference between these original and true is a significant but not very bad, right? Here, when you take m equals to 1, this is okay and better than m equals to 0. When you take this, it is also fine and not very far away. But when you take m equals to 9, oh my god, what is this? It is very far from the true, right? So you are doing very bad when you just bit deviate from the true training data, from the training data set. And it is a variability, right? It is very variable. You never know what you're going to see in this case for unseen data set, and how bad you are doing is also not calibrated. You can't measure that. So the question that I had just asked, like, what is overfitting may not be good, but how overfitting cause a problem is the answer what I'm giving to you on this slide. Is this clear, guys? Can you, because I am over time, I want to just finish the class on this the concept. Do you see like how overfitting cause a problem? Ritvik, you understood, like, because I have stopped you when you were answering, sir.
Yes, sir. I understood.
Fine, cool. So yeah. So any questions before I wrap?
Sir, I had one doubt. Hello?
Yeah, please.
Yes, sir. As you said, a green line is the curve that originated the dataset, and a red line is the best fit module.
Right.
So for m is equal to 3, why is the best fit model different from the curve that originated it?
Very nice, very nice. But you forget that we added a noise to the data set, right? Did you remember this?
Yes, sir.
Rahul, do you remember that we have added a noise also? We are
Yes,
fitting
sir.
noise also.
Gaussian
But
noise.
very nice question.
Yes, sir.
So we had added a noise, and my model is not that very smart. If my techniques are these are just statistical techniques, right? So because I have added a noise, so I am fitting a noise also somewhere. So when I try to fit a noise, so it will definitely move away from the true function, which is the green one. If I didn't do that, my m equals to 3 same what my green is in red, right? But because I've added noise, then that's why there's an effort of passing through a point which was not correctly recorded, and I will deviate myself from the green. Clear or not?
Yes, sir.
Okay. So before closing, I have two questions in the chat box. I just want to read it. Okay. Okay. Ashutosh is asking how to know overfitting happens in our model while training. Very nice question. And I think the simple and short answer is you will get training error 0, right? And long answer, I will address it somewhere else in my future lectures. But I want to know while training itself to save computational resources anyway, maybe 90. Okay, we will discuss it anyway. So in next class, if you have any questions, many major questions, we're going to discuss it, and then we will start our next class. Till then, I hope everything is fine. You drop your questions on the Google Classroom, and you may drop your attendance in a chat box for now. And I'm using some extension toolbox here where your attendance is being recorded. So thank you very much. You can just drop by dropping. You can just exit by dropping your attendance.
Sir, sir,
Yeah, please tell me.
sir. One small doubt, sir. Here, the is the overfit